So I want to take you quickly through my solutions for 3.2 and 3.3. So 3.2 asks us to verify these two identities by writing out all of the terms. So if we start with the definition for the Kronecker delta, we have that the delta is equal to 1 if our indices I and j are equal, and 0 if our indices are not equal. So part A has a Kronecker delta with subscripts equal to 3. So we know because the subscripts are both the same letters, then they're also going to be the same numbers. So if we just consider indices 1 through 3, then we have delta 1, 1 plus delta 2, 2 plus delta 3, 3. Since the indices on those deltas are all equal, the deltas are all just equal to 1. So we have 1 plus 1 plus 1, which is equal to 3. Part B has two Kronecker deltas with subscripts m and n. So again, just assuming we're going with indices 1 through 3, we write out all the individual terms. Here, I'm not going to say it all out loud, it's a very long equation, but essentially we find out that 6 out of the 9 terms equal 0 because the indices are not the same number. Then we are left with these 3, which each have the same indice, which means that the deltas are equal to 1. In each case, 1 times 1 is 1. So we end up with the same thing from part A, 1 plus 1 plus 1, which equals 3. Moving on to 3.3, we're asked to write out in matrix form to the parts from 3.1. So in part A, we had that V sub I is equal to H sub Ji times U sub J. So we know since there's only one index on V and U at most, and assuming we're staying with the same convention of indices 1 through 3, we're only going to have a 1 by 3 matrix for V and U. However, since H has two subscripts and 1 through 3, we have a 3 by 3 matrix for H. So you can clearly see here how that all works out. Part D, we have F sub ij equals a scalar A times G sub ij. So again, we have indices 1 through 3. We have two indices on F and G. So we can write out Fij as A times a 3 by 3 matrix of G with each of our possible indice combinations for I and j equal to 1 through 3.